Hello and welcome to this tutorial. Today I'm going to do a model of the air blast loading over a composite panel, and this composite panel has three layers. The first layer is epoxy glass as a composite material with 16 layers with different orientation for the fiber. The middle layer is ceramic, and the third layer is TPU, thermoplastic polyurethane. For the epoxy glass, we will use Hashing damage criterion. For the ceramic, Drucker-Prager coupled with equation of state, shear modulus, and ductile damage. And for the polyurethane, ductile damage and isotropic hardening. Uh, for the ceramic, we can also use JHB or JH2 model, and we have many tutorials in our website about the JH2 and JHP, but here we will use Drager-Parker and equation of state with ductile damage, and we will consider a TNT here, TNT source, for instance 25 kilograms or more or less. And let me to close this tab. Now let me to create three parts. The first part, E-glass, epoxy glass. It is 3D deformable shell, planar, approximate size 4 meter, continue. Create a rectangle, the first point 0 and 0, the second point 1 and 1. This is 1/4 of the model, of the whole model, because we have symmetry boundary here and we don't need to model the whole parts, just 1/4. Double mid click, this is the epoxy glass layer. Then the ceramic has a middle layer, 3D deformable solid extrusion, this is continue. Create again 0 and 0, 1 and 1. This is the ceramic, double mid click. The depth is 2 centimeters. This is the thickness of the ceramic. The third layer is the thermoplastic polyurethane, 3D deformable solid extrusion, continue. Again 0 and 0, 1 and 1, press enter, double mid click. 8 centimeters, 0.08 centimeter is the thickness. We will use meter for length, Newton for force, Pascal for stress, second for time, and these are our units. Now go to assembly, insert all parts as dependent, auto offset, and OK. Now let me to create some surfaces here. The first surface is TPU. We don't know anything about the interaction between these layers, so we will use tie constraint among the surfaces. Continue, and this is the TPU layer. Now the ceramic top surface. Continue, it would be this. Now use rotation. Create another one. Surface. Ceramic butt surface. Here. Now create another surface. Name is E-glass surface. Continue, select this, the purple, and now create another one, a surface, name is blast. Continue, select here the brown. Okay, now move this part, select it, done, this point to here. Now this part done, this point to here, done. Now select all, done. This point is 0 0 0. Okay, again select all, done. First point 0, second point negative 8 millimeter along zeta direction. We will use 8 millimeter as a thickness for the epoxy glass layers. So Now let me create some sets to consider the symmetry boundaries. So first set name is xsim. Continue, select all. Now press Ctrl, remove here and here. Here. Sorry, this is ysim. Select here, remove here, here. This is the x symmetry. Create another set y symmetry. Select all, remove here and here. This is the y symmetry. And now create a set name is fixed. Select all, remove here just those areas. Okay, I'm done. And now let me to remove this ceramic. Now create a set name is u. Continue, select this point and done. Okay, everything is done here. Just create two reference point. First at 0, 0, 0, second 0, 0, 0 0.2, 20 centimeter. Here this is the detonation point. Go back to material. First in the material, let me check the Abaqus documentation. The Abaqus documentation, the example manual, the dynamic stress, and this is the model. Okay, here is the definition of the ceramic and also the brittle material. The Johnson-Helmquist bezel, Johnson-Helmquist. We can use this too. Also, we can use Prager plasticity and equation of state in Abaqus explicit to demonstrate the behavior of the brittle materials. So let me check the Prager model here. It says we use a calibrated Prager plasticity model and an equation of state to obtain a material behavior that is similar to the JH2 model. We have JH2 and JHP on our website. So here the strength parameter of the Prager with this equation, and we will have this constant AB. These are the constant of the material, and also the damage. The paper used ductile damage initiation, but if you notice the um, Abaqus documentation after version 2020, it used Johnson-Cook rate dependency for the ceramic, but in the previous versions like 2014, it doesn't say anything. Also here the pressure equation, which is defined as the equation of state like this, and if you click on this you will have the material data for the ceramic silicon carbide Prager. This is the equation of a state here. You can, these are the constant, the elastic as a shear modulus Prager exponent format. These are the values, and then Prager hardening compression. You can see that, and then the Johnson-Cook rate dependency, and also the density and the damage initiation, ductile damage, and also damage evolution, something exponential, zero. These are the material for this, and also for the TPU, thermoplastic polyurethane, we have the material. Um, let me check the material for the polyurethane. Here is the material for TPU, the Young model, Poisson ratio density. These are the ductile damage components. Then the isotropic hardening for the TPU here. You should use these materials here. And then the e-glass as a Hashing damage criterion. You can see this is a definition of the Hashing damage. We have two types of Hashing damage criterion. The first type, the alpha is 0, and the second is alpha is 1. And this is the fiber tension, fiber compression, matrix tension, and matrix compression. And this XT is here, longitudinal tensile strength here, again longitudinal compression, and the other. You can see this is the data. Now let's me to enter the material from my library. TPU, e-glass, ceramic. Let me check them. First the ceramic. So the density, 3,215 kilogram per meter cube, or 3215 kilogram per meter cube. Elasticity, elastic. The shear modulus, then the plasticity, there are Kerr-Prager, the exponent form, these are the constant, and then the Prager hardening, this is the value, compression. The new release of Abaqus says you can use rate dependency, Johnson-Cook, something like this. Already we don't have this permission to use Johnson-Cook for Prager, but here in the version 2020 we can use. You can use that as the optional thing. Also you can remove it, no problem with this. And then the ductile damage, and these are the value, and also the damage evolution, exponential, softening, the fracture energy is 0. Okay, this is the, sorry, the last thing is equation of state, USUP. This is the sound velocity, and these are the USUP variable. Okay, click on OK. Then the epoxy glass, the density 1506 kilogram per meter cube, elasticity as a laminar here type, Young modulus in plane, Poisson ratio, and shear modulus, and then the damage, Hashing damage criterion, the alpha is 1, and these are the values from the paper, but the paper doesn't say anything about the damage, and we use also the damage data for the tensile fracture energy, compression fracture energy, and transverse in tensile and compression fracture energy. Okay, and the last thing is TPU, the density 1115 kilogram per meter cube, elasticity elastic, Young modulus, Poisson ratio, and then the plastic as a plastic isotropic. These are the data, and you can see this is a high value for the plastic strain. And the last thing is the ductile damage, like the paper. Okay, create a section TPU as the solid homogeneous material is TPU. Remove this set, assign it. Okay, then the ceramic or silicon carbide solid homogeneous material ceramic, assign it to this part. Okay, and now the e-glass with for now 8-layer conventional shell. Right click here, edit region, select it, done. Right click here, edit material, epoxy glass. The thickness is 0.5 millimeter, totally 8 millimeter. Dilation angle 90, sorry, rotation angle, and this is 60, 30, 0, 0, negative 30, negative 30, negative 90. Now select all poly here. Use symmetry to make it 16 layers. See, 16 layer. And the offset is bottom surface, and the axis 3 is a normal, the top. We can use also polystack view of this, of the fiber You can see the red signs, the fiber, and these are the matrix. Okay, now go to here. Here we can use tools, assembly. Before that, use part instance, use render shell. You can see here now. These are the parts. Okay. Now go to a step. In the step, because of the TNT explosion and convert method, let's me to use explicit step. Continue. The time is 0.002 second or 2 millisecond. You can increase that or decrease that. We can use also mass scale to accelerate the simulation, but here we don't need it. Edit the field output, request 100 interval, remove the Eulerian and redundant requests. Here for the force request in convex force pressure, then the failure damage criterion, also these two for all components, and use a status to remove failed element in the visualizations. Define a story output to get the reaction force. Continue. For the set name is fix, sorry, 500 as an interval, reaction force RF3. We model 1/4 of the whole model, so if we got the reaction force, we should multiply that by 4. We should magnify that 4 times more, because we model 1/4 of the whole. So the output 3 is the U, 500 displacement U3, and okay. Now go to interaction. In interaction we have tie constraint. If we know anything about the interaction between the layers, we could make the cohesive interaction, but till now we don't know, so I prefer to use tie constraint. The surface, for instance the bot ceramic with TPU, okay, then the top ceramic as a master with e-glass, okay. And now let's me to define the TNT property as the incident wave. Continue as a convex. The mass is 25 kilograms. This is too much, but that's okay. Now in the step 1, in the step 1, use incident wave. Continue. Source point, a standoff point, and the blast surface is the blast. It is convex, time of detonation 0, and this is 1. Now the blast energy will arrive to the top surface immediately. So here we should create 3 boundaries. The first boundary is X symmetry. In the step initial, continue the set X symmetry. Select this. Now create Y symmetry. In step initial, continue, select Y, and OK. And now create fixed. And it is in cast fixed in all the direction, and these are all things that we need. So click on part. For the ceramic, use 15 millimeter, and for here select it, press Ctrl, remove here just the thickness, create 3 elements, mesh part yes, element type explicit, 3D test, linear reduce integration, and element dilation yes. For this also use 15 millimeter, mesh part yes, explicit shell, radius integration and element deletion, yes, okay. And for now use 15 mm mesh part, yes. Element type explicit, 3D stress radius integration and element deletion, yes. Okay, now everything is good. Just let me to create job 2 from model 2, okay, and submit it. Already I did this simulation, I did this, and it's completed. And just let me check it for the possibility error. If we don't have any error, I will kill it. Okay, it is good and it will be run without problem. So let me to kill it, and I will check the result for the previous analysis. You can see it is okay. So here, let me check it. This is model 1 for you, and this is model 2, and this is model 1. Already I did this. So the model 1 has 3 parts: ceramic, glass, TPU. The material is the same: ceramic, TPU, glass. Assembly is the same. The step is good. The interaction, the tie constraint, and the boundaries, and the mesh. We use the finer mesh for ceramic here just. And let me check the manifold for this. You can see it takes 1500 seconds to complete this 2 millisecond here. Let me check the results. And from viewport to viewport, show maximum minimum. This is 8. Make also this 8. Also this. And okay. And let me click on this. And you can see the damage which happened and the failure of the ceramic. You can see this is the polyurethane with large deformation. From view, ODB render show thickness. This is the upper side. Let me to click on animate. You can see the deformation and the damage which has happened during the explosion or the blast load. The ceramic is a brittle material. See the failure of the ceramic here and here. You can see it is failed completely failed, because the mass of TNT is too much. 25 kilograms too much, and it is failed completely. You can see that. Now let me request, for instance, the damage for all parts. See the damage for all parts, for the composite, for the ceramic. You can see. Okay, now let me request from view ODB mirror to make it full in this view. And now let me replace the part, for instance, e-glass. See the e-glass, it is filled completely. And let me check feature edge here. Animate. For this we can create request compressive damage for the fiber. tension damage for the fiber, compression damage for the matrix, and tension damage for the matrix. These are the outputs. Also the in-conweb blast pressure, you can see. Okay, now let me replace the part in ceramic. See the ceramic, the brittle behavior, and the cracking and crack grows. Let me request the damage. And this is the ceramic, you can see it. Now let me replace the polyurethane. See the damage and the deformation. Ductile damage, plastic strain, de-stress, or anything else. We can request anything here for the model. Also here from the story output, continue. Reaction force, select all the reaction forces for 1/4 of the model, not whole, for 1/4. Sum and plot and OK. And this is the reaction forces for this explosion. So, if you need to model ceramic, plexiglass, polyurethane, you can use this tutorial and the material data and anything else. But if you want, you can change the geometry, step interaction, load, mesh, or anything else. And also, if you have any questions, contact me on abaqusfm.com at gmail.com. I will answer your question there. Thank you for your attention.